Welcome to this video, one of the many in the Secure Your DNS, Secure Your Network series. My name is Tim Rooney, Director of Product Management at Diamond IP from BT, and the goal of this video series is to break down into bite-sized chunks the many ways that the domain name system, or DNS, can be attacked or manipulated for nefarious purposes, and the defensive measures that you can take to help secure your DNS and therefore better secure your network. In this video, we're going to talk about DNS security extensions, or DNSSEC. We've actually broken this topic into two videos, and in this video we're going to talk about resolution. We'll start off with what problem DNSSEC is trying to solve. DNSSEC is defined in several RFCs, namely initially defined in RFCs 4033 through 35, and there have been several other RFCs since then addressing DNSSEC topics. But these RFCs provide the foundation for basically how it works, the different resource records that are involved, etc. But I will highlight one of the subsequent RFCs, 4641, talks about operational practices, which is also informative for those of you looking to really understand why there's different keys. And we'll talk a little bit about that here in this video, but just for further information. So basically what problem is DNSSEC trying to solve? It's trying to authenticate zone information, resource record information. So when I query for a given web address and I get an answer back, DNSSEC allows me to authenticate that answer as having been signed by the domain administrator responsible for that zone. So let's say I query for www.example.com, I get an answer back, it's got a signature on it, and that signature enables me to validate it as, yes, indeed, this was published by the example.com zone administrator. Data integrity means that information was not tampered with between the time it left that server, the example.com server, and reached my resolver, my validating resolver. So it gives me that origin authentication as signed by that administrator and provisioned by that administrator of that zone. It hasn't been tampered with en route to my resolver. And third feature that DNSSEC provides is authenticated denial of existence. And what that means is that if I were to query for a legitimate web address and I get an answer back from an attacker saying, no, that record doesn't exist, an NX domain, I might actually believe that and think, well, that web address is down or otherwise doesn't exist for whatever reason. I might go to another site, a competitor site, or what have you. What the authenticated denial of existence provides is the ability to come back and say, well, yes, that record you're asking for does not exist, and by the way, I'm signing this to authenticate the fact that it doesn't exist so that you won't accept an unauthenticated denial of existence. So if somebody does attack DNS and say that doesn't exist, you can authenticate that. And we'll talk about how this process works as we go through this video. But let's take a step back and look at just the basic DNS resolution process. And let's say I've got my resolver, which could be a laptop, a phone, etc., whatever device on the left of the figure here. And when it's configured to operate on a network, it gets an IP address, typically through DHCP. And along with that IP address for the device itself, the DHCP process also supplies a couple of DNS server addresses that my resolver can use to query in order to find the answer to certain domain names that I want to look up as a user. So the recursive server is really the server that's going to go out and find the information on the internet, should it not reside in cache, which is the case here. So if I make a query for www.example.com, it doesn't reside in cache. I'm going to go to the hints file on that recursive server, which basically is the server names and IP addresses of the internet root DNS servers out there. I'm going to select one, make a query there, and that server is going to indicate that, okay, I don't know the answer to www.example.com, but I do know what the COM servers are. So it provides a referral back. Likewise, you issue the query to the COM servers. It too does not provide the answer fully. However, it does provide the referral to the example.com's administrator DNS servers and IP addresses so that the recursive server can now make the query to one of those servers. So the process of going down the domain tree is one of locating authoritative servers that are responsible for that zone, and then issuing a query to one of those servers to actually query for the question at hand, in this case, www.example.com. In this case, I located an example.com DNS server. I get an answer back, 192.0.2.54. Information is cached in my recursive server, and the information is passed back to the resolver, who then is able to make the connection ultimately that I was intending to make. So you can see how DNS provides that translation from what I want to get to from a text perspective, www.example.com, converts that to an IP address that my computer can now use to connect over the internet. Now, once that information is cached in that DNS server, the next person that comes along asks the same question. Well, it basically just hits the cache and I get an answer back right away, and I'm able to connect to that web server as well, or whatever server I'm trying to connect to. So you can see that the caching definitely would have an improvement in the performance. I don't have to go out to the internet, make the query to all those several servers, which in and of itself doesn't really take all that long. However, with several queries and a lot of outstanding queries on the internet, it can add up. So having that information cached is definitely a big performance saver and really one of the key elements of how DNS works in general. Now, if we look at why we need DNSSEC, and we look at if information is not authenticated, what can happen here. So here, let's go back to our example. Let's say I, again, query for www.example.com. My recursive server locates the authoritative server down the tree. We'll leave that part out for now. But now I've located my authoritative server. I issue my query to that server, but an attacker is able to come back before I get the legitimate answer, and my recursive server matches on several criteria, as we'll talk about in a moment. And it basically believes that answer, 198.51.100.71. So my recursive server caches that information. In the meantime, my authoritative server may respond, but I've already got an answer, so I'm just going to ignore that and drop that one in the bid bucket. But I'm going to pass along the first answer I got that matched, well, the attacker's IP address, and therefore my device will connect to that attacker server. So you can see how this process of providing an answer back to a recursive server can redirect a resolver to an attacker site, and it can basically be set up to look like the site you're trying to get to. They can try to get sensitive information from the resolver, etc. So it can have disastrous consequences here. So that's the goal of the cache poisoning case, and we call it cache poisoning because not only have I manipulated the answer for that particular client, but should another, again, resolver comes along and asks the same question, again, I'm just going to, as I did before, just look in the cache, and then all those resolvers that ask that question, whereas www.example.com, and get redirected to this attacker website during the length of that record's time to live, or TTL. So as an attacker, I can set a very long TTL. If I manage to poison the cache, you can see why that term applies here, because I've basically got my answer into the cache on that recursive server. Anyone asks the same question, I can then just provide that answer back and also redirect all these other queriers to my attacker website to gather that information. And there's other forms of cache poisoning where you can manipulate the name servers. But just to look at the recursive server in terms of what it's looking for, it's not just going to accept willy-nilly an answer that happens to match the question. It's looking at several elements here. Certainly the IP address. If I locate the authoritative server and send a query to that server, I'm going to filter my response for that question based on the IP address that I sent it to. IP addresses can be spoofed, and thereby an attacker would need to spoof the IP address of the legitimate destination IP address. They'd also have to match on the user datagram protocol port numbers. So here we're kind of looking at the packets, the query sent on the left, and that on the right. We've got the IP header on the top and showing an IPv4 header kind of grayed out there, and then except for the source and destination IP address and the ports. And then we get into the UDP header field below that, and then looking at the UDP port numbers, that would have to match on what I sent and what I'm receiving from a converse perspective, just like the IP address. The transaction ID, this is within the DNS header, where I'm looking at the transaction ID that I'm sending out, so that it's got a way to kind of map the query to a response coming back, and that has to match as well. Also the name, class, and type. So basically what my question was. So typically a question is framed in the form of the QName, www.example.com, the class, which is typically internet, the type, let's say I'm querying for an A record or an IPv4 address. So that all has to match as well. And then I've got to check what's called a bailiwick. And that means that my example.com answer comes from a name server, as shown in the authoritative section, that is also responsible for that section of the domain tree. So my answer coming back for example.com shouldn't be coming from attacker.net, for example. So it needs to come, or at least look like it's coming from the same authoritative section of the domain tree. So you think about, well, I've got all these criteria. It must be very difficult to attack it because I've got to get an answer back before the legitimate server responds. However, there have been several mechanisms that have been shown that UDP port numbers and transaction IDs can be really rifled through very quickly and provided an answer back. And then the Kaminsky vulnerability, which was pointed out over 10 years ago now, indicated an easier way for an attacker to instigate a query by perhaps putting up different hrefs on a web page if they're able to get the user to go to a certain web page. And they basically, when you go to that page, your resolver is going to look at every href tag or source tag within that page and try to resolve that to get the content that's referenced, and thereby an attacker can make your DNS resolver query for a bunch of known names. And so it can basically provide answers back once it detects that resolver has hit the attacker web page. So it's a way for an attacker to, in essence, instigate the query and provide answers back, and that helps with the timing. And it also is a way where they can provide information back in the authority section that really repoints the entire domain tree to their name server, so they can change those servers, maybe provide a bogus answer back, but also provide the name server for that branch of the tree. So future queries for anywhere below example.com, for example, can be directed to the attacker sites, because it's not only the answer that's cached in the recursive server, it's also the authoritative information, so that if I do have a query for example.com, let's say it's mail.example.com, I already know the name server for example.com. I don't need to go up and down the domain tree. I already know where that name server is. I can just query it directly, saving some time on the query performance. And therefore, the cache poisoning attack that addresses the authority section can also have wide-ranging impacts. So, to address this vulnerability, the DNS security extensions was defined, and it provides a mechanism for administrators to sign their zone information, and also a way for those resolving information on the web to get signatures back to authenticate that information. So let's take a look at how that process works. Let's say I've got a very simple zone file here on my left. I've got an A record in there and a mail exchanger record, very simply. And we're going to go through a very basic example here. I'm kind of leaving out a lot of the details just to illustrate the process. But basically, the example.com administrator administers this authoritative DNS server, needs to generate a pair of keys. A lot of DNS vendors, all the DNS vendors basically provide key generation utilities. You can create a key pair, and we'll talk about that in the next video about why you would use a key pair. But basically you have a zone signing key which signs the zone information, and then a key signing key which signs the key information. And the key signing key is generally a longer key. It doesn't expire for a longer time because it's more expensive computationally, and for that reason it's not used to sign all of the records in the zone. So you've got this trade-off between a zone signing key, which is shorter, more nimble, can be more quickly calculated for performance reasons, but also can be changed more rapidly. And then you've got a key signing key, which, as we'll see, is going to be the key that my recursive server is going to track to validate the signature. So the way this asymmetric cryptography works basically is you've got a pair of key pairs where, let's say, my private key, one of the components of the pair for each, is signing the zone information, and then actually publish the corresponding public key, which is cryptographically mapped to the private key, and that information is passed back with the answer, as we'll see, and is used to validate the signatures and to confirm that that key was used to sign that information. So once I've got my zone information signed, I've got it loaded on my authoritative server. The recursive server needs to know what that key is, and they need to, it's called a trusted key. because it's basically I've set up a relationship with this example.com administrator, and they've provided me, okay, here's the public key that you can use to validate the signatures on the information that I'm going to sign in my zone. So now when my query comes in for example.com, the recursive server goes through its normal process, locating the example.com authoritative DNS server, locates one, issues a query for that information. In this case, if an attacker comes back, even if they sign their information back, I don't have that key as a valid key, or it doesn't map into my chain of trust, which we'll talk about in a moment. So I'm going to consider that information bogus, even if it matches on all the other criteria we just talked about, IP addresses, ports, transaction ID, bailiwick, etc. So when I finally get my legitimate answer back, it's going to check the key, it's going to validate that, and then pass that information back. It's going to cache it, of course, as well. So what DNSSEC does here is it enables my recursive server to authenticate the answer that I got back as being published by the example.com administrator, and also to validate that it hasn't been manipulated in transit on the way back to me. And thereby I have some confidence with my resolver that it can now, this is the accurate information. Now, when we talk about having the key for example.com, if you can imagine having to have the key for every zone administrator out there on the internet, obviously that's in the tens or hundreds of thousands, clearly not something you want to do. So fortunately, the DNSSEC chain of trust was defined basically to mimic the domain tree. So we've got the internet root is signed, and then there's a mechanism to really chain that down to the example.com zone. So let's say, for example, I want to issue another query for www.example.com, and I'm going to go down the domain tree once again. Let's say I get to the example.com server and I get an answer back, and that information's signed. Now in this case I don't have the key for the example.com because I'm going to rely on this chain of trust. So I get the answer back, it's signed, the signature validates, that's great, but I don't necessarily trust the key that the example.com administrator used. So let me ask .com about that, and this is typically done on the way down as you resolve the information. This information can be provided, so there's not technically a query back up the tree. It's kind of gathered on the way down the tree to locate the example.com server. But from a logical perspective, we're just illustrating this here. So the .com information, yes, I can validate that the example.com server key is valid as I'm signing it myself, and that's the delegation signer record, which basically is a hash of the key signing key of the example.com zone. So it's basically saying that, yes, that is a valid key, and I'm validating it by signing it myself. However, I still don't trust the key that .com used. So I need to go up one more layer to the root, and I have the information back, yes, this is the correct key used by .com, and I'm vouching for that. I'm also signing it with my key. And by the way, here's the DNS key for the internet root. And then the recursive server basically matches that, everything checks out, and provides the information back. So in this manner, you only need to keep track of the public key of the internet root, and thereby through this process of this chain of trust, through these delegation signer records down the tree, you can actually authenticate that information by using a single key. As long as that all the signatures are valid and the DS records match the child's key signing key, then everything maps from a cryptographic perspective. So this simplifies on the recursive server side having to manage a lot of keys. You've really just got the DNS key from the root that you need to track and keep up with, and then that can be used to validate all subsequent signed zones. Of course, they all have to be signed. That chain has to exist all the way signed down to the point where you're resolving. But if that's the case, you can validate in that manner. So that simplifies the recursive server management quite simply. Now, in terms of the authenticated denial of existence, we talked about this where I could query for a www address, and then the attacker can come back and say, no, that doesn't exist. Don't bother looking here. But in this case, I want to be able to authenticate that answer so that that doesn't happen. So there's what's called a next secure record, NSEC, And what that does, it basically shows you here in this example on the right, I've got a record a.a.net is my resource record. It's an A record. I've got a signature on that. And then I've got an NSEC record saying that the next record canonically in this zone is b.a.net. And it in essence points to that next record, and that record NSEC points to c.a.net, and so on. So if I were to make a query for a1.a.net, that record doesn't exist in this zone. So I would respond back that no, it doesn't exist. And by the way, the next record between a.a.net and what you're asking is b.a.net. So you're asking for something that is not in that gap, therefore it doesn't exist, and I'm authenticating that. So that enables the bypassing of the issue where an attacker can illegitimately say something doesn't exist. Here you can legitimately say that, authenticate it, and provide it back. So as you can see, this information in the NSEC record makes it pretty simple for me to identify what are the records in the zone, because I can just kind of subsequently query for each NSEC record to get the next in the chain and thereby footprint the zone, so to speak. So if that's considered an issue, you don't want to allow people to easily perform reconnaissance, there's the NSEC3 record, and that basically provides a hash of the owner name, and the owner name is that field on the left here, b.a.net, for example. So there's a way you can hash that several times, for example, use assault, and basically define the next hashed owner name in the file in order to be able to make that a little more difficult to footprint the zone. It's not impossible, but it just makes it cryptographically more expensive for an attacker to do that function. So in this manner, DNSSEC provides the authenticated existence or non-existence of a record, and also the data integrity and route. And then our next video in this series will talk about the administration of DNSSEC